without exiting the loop because it is an operating system concept to close an application. So that comes pretty close to an infinite loop. If you have a control application, sometimes that's also an infinite loop because you keep doing it until the thing is powered down. So or they have hardware methods of shutting down the system instead of using software to shut down the system. So that means in software you can also have an infinite loop.
Some robotics like that.
In robotics, yep, robotics or factory.
Thing and then it does it again.
Well, it goes in. It kind of gets stuck in an infinite loop of doing the same thing. It's quote unquote doing the same thing, but what you do inside the loop, depends on the application of the robot. Okay, very good. And there are also applications where the application itself will terminate abruptly without even having time for the software to shut down anything. So in those cases, you also don't have to worry about when do I get out of a loop. I just thought of one application. I was reading this yesterday. The U.S. Army now has this smart grenade launcher. Have you guys heard of that? No? Okay.
they pull out the pins before they throw up?
Almost. Okay, almost. I can see certain certain risks of that particular device. So anyway, it's a rocket launch. It's more or less a grenade launcher. Okay, I think it's called the XM25. You guys can look it up online. What it is it has a range finding apparatus. And so when a soldier aims that thing, it will find out the range between the weapon and the target. Okay, the target can be a building, can be something, a window, a door, or something like that. Now, the interesting part is it is programmable. Okay, so the soldier can actually program the grenade to explode. In I think 3 meter increments. Can control do we want it to explode right at a target, before the target, or after the target? Okay. In other words, you can make the grenade explode 3 feet behind the a window or a doorway or something like that. Okay. Are we doing okay so far? Mm-hmm. So the way it works is there's communication between the weapon and the payload and the grenade. So the weapon can tell the grenade, when to explode, because the grenade needs to know, okay, how much have I traveled, and then if I have traveled this much distance, then I'm supposed to go off, right? Now that opens up a certain type of risk, right? Because if someone can convince the grenade to go off right after it exits the muzzle, then it will just it would not be very good for the person who's launching it. Okay, so whenever there's control involved, and whenever there's a control element like that involved, there's always a risk of that thing can get tricked to harm the person who's launching it instead of the target. It's just like with missiles. Right? Missiles have quote unquote intelligence. They know where to go, either by guidance by a radar or by heat signatures and whatnot. But whenever it has intelligence, it also means that it can be tricked, and that's why you have the flares and the shafts and stuff like that to fool the missiles into hitting something that is not supposed to, or to chase after something that is not the actual target. But when you think about the 16-inch guns from the good old battleships, there's no tricking those shells, right? Once it leaves the barrel, it's going that way. There's no recalling or telling it to stop anymore. So it's the same thing. But getting back to the loop, infinite loop, concept, the grenade that gets launched from the gun, if it has software running on it, it can be an infinite loop because there's no need to shut down that grenade software using a software, because when it goes off, that's nothing else to run the software on. Yeah, those things are, if I remember correctly, $25,000 each. The weapon itself is $25,000 each. Well, but if it can help the Army, I guess it's worth it. It depends. I hope they don't have a bug on that thing, like software bug. Whenever you have complicated applications like that, there's always a possibility that there's a software flaw somewhere. Okay, and software flaws like that in the battlefield is not going to be good. Okay, so in this case, in a search algorithm, when do I want to get out of the loop?
Maybe when AI equals K.
Okay, so you're actually a few steps ahead of me. That's good, very good. But in terms of just vaguely describing the search algorithm, when should we exit? Go ahead.
When you find the word you're looking for, or at the end of the array.
Or at the end of the array, but you're also you're still ahead of me. Does anyone want to describe it even in vaguer terms? I want something that is vague. Yep.
When you found it, or sure you haven't found it.
Okay, very good. So I can say that when the value is confirmed in the array, or the value is confirmed not to be in the array. Now, the reason why I want to make it more vague than some of you have already suggested is I just want to show you how to work on an algorithm really step by step. We don't even start thinking in terms of arrays or comparisons or anything like that. We think in terms of the higher level logic, abstractly. When do you get out of an algorithm whose job is to search for a particular value in an array? Well, I guess we can leave when we can confirm it is there, or we can confirm it is not there. Okay. So the next one, in the next revision, I will name all these. This is revision 1. In the next revision, we'll basically think about can we use variable names, in this type of algorithm. So we can basically say assume K is the value we are looking for. Assume A is the array that we are searching in. So that means, at this point, I can change the pseudocode a little bit to make use of the variable names. When I say the value is confirmed in the array, then we can say, oh, well, exactly, as what you guys said, when a bracket I for some I don't know what I is supposed to be at this point, but if I can find an element a bracket I that has the value k, that tells me that I can exit the loop right away, because I have just confirmed that it is in the loop. In the array. I don't quite know how to say that the value is confirmed not to be in the array, but instead of saying that, no, you cannot say that, because if you're okay, let me explain that. One of the suggestions was, what about I can say that won't work, because all that is doing is confirming that the element that you're looking at right now does not have the value that you're looking for. It does not confirm that the rest of the array does not have that value either. Okay? Does everybody understand why we cannot use this condition to mean the value is confirmed not to be in the array? Because the highlighted condition confirms that one element does not have that particular value. It does not confirm every element in the array does not have that value.
Can you say when the last index of the array is not
You can, but that depends on the search, direction. Because if someone is searching from the back to the beginning, then you have to change the condition, right? So I'm not going to include that until I have talked about why do we want to search sequentially from the beginning to the end. But you are absolutely correct. You're ahead of me already. But I do want to explain that part. So for now, we'll just say that we don't know how to express the fact that the value is confirmed not to be in the array. Okay. In revision 3, we have to determine, do we want to search sequentially? Do we want to start with the beginning, scan all the way to the end? Or do we want to start from the end, scan all the way back to the beginning? Or do we want to search in a random fashion, okay, or pseudo-random fashion? Okay, what do I mean by pseudo-random? Pseudo-random is easy to do. Let's say we have 8 elements. If I have 8 elements, if I want to visit or if I want to look at each and every element, one way is to go from A bracket 0 all the way up to A bracket 7. 0, 1, 2, 3, 4, 5, 6, 7 in a sequential manner. I can also do it in a backward manner, which means I start with A bracket 7, then I go 7, 6, 5, 4, 3, 2, 1, 0, and I'm done. But I can also do it in a pseudo-random way. If you want to do it in a pseudo-random way, all you have to do is to find a prime number. In this case, I'll use 5 as a prime number. Okay? So we can basically say every time I do it, I skip by 5. If I skip by 5, I can still use A bracket 0 to begin with, although it is not needed anymore. Then the next one is A bracket 5 because I skipped the 5 elements in between. The next one seems to be kind of troublesome because 5 plus 5 is 10. 10 is more than 8, or more than 7, so it doesn't seem to work. But I can wrap around. In other words, when I see 5 plus 5 is 10, I can say, oh, I can wrap around from the beginning again. So that means the next one I'm going to look at is A bracket 2, because 2 is 10 minus 8. Then the next one is A bracket 7, because I'm skipping by 5 again. 7 plus 5 is 12. 12 minus 8 is 12 minus 8 is 4. Then 4 plus 5 is 9. 9 minus 8 is 1. Okay. 1 plus 5 is 6. And then we have 6 plus 5 equals 11. 11 minus 8 is 3. And then we have 3 plus 5 is 8. 8 minus 8 is 0. So we are back to the beginning. In other words, if you choose a prime number to skip by, which is different from the number of elements in the array, you are guaranteed that you will visit every single element if you just add that much, or if you skip by that. If you skip by that much when you go through the array. Okay. So the question is, which way is better when we search in an array that is not sorted?
Does it make any difference?
Yep, exactly. That is the question I'm asking. Does it make any difference? When you look at the software perspective, it does not make any difference. I can skip by 7. 7 is a prime number. I can skip by 3. 3 is a prime number. I can even skip by 11. Now you can say 11 is more than 8. How can we do that? Well, since we can always use the wrap around method, skipping by 11 is not a problem. I can skip by 13. I can skip by, any prime number, and it will still work.
In this case, you will start with 3. You're going to skip by 11.
Yeah, if I skip by 11, then it will go from 0 to 3, and then 3 plus 11 is 14. 14 minus 8 is 6, and so on. So skip by 11 is basically the same as skip by 3 because, 11 mod 8 is 3. Okay, very good.
I think in this case, you either want to go backwards or forwards if you're not sure how many elements you would have.
You can always say, this is the very first index that I have. When I get back to this index, I'm done. So it's a little bit more cumbersome, but it can be done. Okay, the little details is a little bit more complicated.
If you say you were skipping by 5 and we have to have 5 in the array, then
Right, you have to choose a prime number that is not the same as the number of items in the array. Yes, but even that can be done. I can have 2 alternative prime numbers. I just have to do a comparison first. If the number of elements in A is this first prime number, I choose the second prime number. So with 2 prime numbers, I can already handle that part. So in software, we can choose to do it in a random way. That's actually perfectly fine. But how about your processor? Would it make any difference in terms of the execution speed of the algorithm? That's the question. Okay. Do you guys know what is the cache of a processor? Okay, sort of. You understand it more. The more cache, the better, right? Because it can keep more